Alright, so today I'm going to explain momentum. Now, I will be using some calculus, so I recommend you watch my video on short integrals. But nevertheless, let's get started. Momentum is a measure of an object's tendency to remain at a constant speed. Now, we denote momentum using the variable p, and we calculate momentum by multiplying an object's mass, in kilograms, by its velocity, in meters per second. So momentum is measured in kilograms, meters per second. There is no fancy unit for it like force has newtons. Now, momentum is the reason that if you roll a ball down a hallway, the ball will continue to roll down that hallway. It is the explanation behind an object in motion tends to remain at motion, and an object at rest tends to remain at rest. Now, there is another part to Newton's first law, and that is, unless the object is acted upon by an outside force. So, the reason the ball eventually stops rolling is because the frictional force with the ground and air resistance act as forces against momentum. So, momentum can be changed by force. Now, an important thing about momentum is that momentum, like many things in physics, is conserved. So that means that if we have two objects that collide, the momentum of those objects is the same before they collide as it is after. So, to look at this, let's say we have a box over here of mass 3 kilograms that is moving at 5 meters per second. And we have another box over here of mass 2 kilograms that is not moving. Now, the combined momentum of both of these objects is we can simply take mass times the velocity of the first object plus the mass times the velocity of the second object. So, 3 times 5 plus 2 times 0, well, that we get 15. So the momentum of this system is 15. Now, these two boxes end up colliding with each other and sticking together. So they now have the combined momentum of 5 kilograms. Now, what is the velocity that it's moving at? Well, we can calculate that. So, remember that momentum equals mass times velocity. Well, we know our momentum, 15, because it's the same from up here, and we know our mass, 5. So, plugging those in, we have 15 equals 5 times the velocity, simply divide by 5, and we find out that they are moving at 3 meters per second. So, you can use the principle of momentum being conserved to calculate the velocity of objects after they have collided. Now, another important thing to mention about momentum is that momentum is a vector. This means that the direction the particle is moving matters. Now, momentum is a vector because velocity is used to calculate momentum, and velocity is a vector. So, what this means is, say we have a particle over here, traveling with momentum 1, and we have another particle down here, traveling in this direction with momentum 2. Now, let's say that these two particles collide and stick together. Now note that when objects collide, they do not necessarily need to stick together. They could very easily bounce off. However, having them stick together makes calculations easier. But nevertheless, we'll say that these two objects collide and stick together. Now, to calculate their momentum, we cannot simply add their momentums, like we did in the previous example. And this is because they are moving in different directions. To calculate their momentum, we're going to look at this as a triangle. So, here, for one leg, we have the second momentum. For the another leg, we have the first momentum. And to calculate the momentum of the two combined objects, we need to calculate the length of the hypotenuse. And to do this, we will use Pythagorean's theorem. So, without going through the entire process, the momentum of the combined particles is the square root of the first momentum squared plus the second momentum squared. But the key thing is that momentum is a vector, so direction is important. Now, momentum can change. And to represent a change in momentum, we write the Greek letter delta, which looks a bit like a triangle and indicates that something is changing, and then momentum, as represented by P. Now, a change in momentum can be referred to as an impulse, and an impulse is represented by the variable J. Now, as I mentioned earlier, momentum is changed via a force. So, our change in momentum is equal to the integral of a force function, f of t, with respect to time. And time is represented by the letter t. Now, it is important to take the integral of force with respect to time, because this is in case we are applying a force that changes over time. So, say we're pushing a really heavy box. We start pushing it with a lot of force, but as time goes on, we get tired and we push it with increasingly less force. So, if we can model the amount of force we use to push that box, we can plug it into this equation and figure out that box's change in momentum. Now, if the force we are applying to the object happens to be a constant, then we can simply ignore the integral and write it as force, again, if it is a constant, times time. Now, let's give an example of how to go about calculating change in momentum. So, going back to our ball at the beginning, let's say that I push it with a force equation represented by 6 times t squared. So this is the amount of force I'm applying to the ball as time elapses. Now, I push it from time t equals 0 to time t equals 1, so I push it for 1 second. And it starts at a momentum of 0, and we want to calculate the momentum it ends up on. So, we're going to take the integral of my force equation, so we're taking the integral of 6 times t squared, and we're taking it from time 0 to 1, and this is dt. Now, the integral of this, that is 6, so we have 2 times t cubed, again from 1 to 0. So 2 times 1 cubed minus 2 times 0 cubed, we can just ignore this of course, so 1 cubed is just 1, so we find that it has a change in momentum of 2 kilogram meters per second. And since it started at a momentum of 0, its final momentum is 2 kilogram meters per second. And that is the momentum that the ball is rolling at. Now, something interesting I'd like to point out is that when I push the ball, it can be essentially looked at as though I were colliding with the ball. But this brings up the question that if I collided with the ball, why did I not start moving backwards some to balance out the ball's momentum? Well, this is because the force of friction kept me stationary relative to the Earth. However, the momentum was not generated out of nowhere. It actually came from the planet itself. So the planet had a slight change in velocity in the opposite direction. However, because the planet is so massive, this change in velocity is minuscule, what would be called negligible. The point of this is that whenever a force causes an object to have a change in momentum, that momentum is not generated or lost. The object applying the force actually has a slight change in momentum. However, this momentum is so small that it can be ignored. But, nevertheless, I hope you enjoyed it, and see ya!